feel like the average person probably is not thinking clearly about what is the worst case scenario around safety and having their data protected. So can you talk me through how you're thinking about that?
Thanks for having me. I'm Ajay. I'm a professor at Boston University. I'm also the CEO and co-founder of Ciphersonic Labs. It's a data security and privacy company. So I have been designing computing systems for more than 20 years now, and it's been a fun ride so far.
We're very excited to have you here today. You are someone who has spent over 15 years in this industry across silicon photonics, GPU architectures, different accelerators. I would love to get your high-level perspective of how you perceive the LLM race today.
It has become an arms race, to be really honest about it. Over time, as the AI model sizes increase, the requirements for communication increase, the requirements for memory capacity increase. And so NVIDIA came along and said, oh, we'll build these NV links, which gives me direct GPU to GPU communication. I don't have to go through CPU. I can get this nice high bandwidth where we could get direct communication between this GPU and neighboring GPUs, HBMs, but bandwidth was still not enough. So we started seeing switches where each GPU could connect to multiple other GPUs through a network switch. Around the same time, wafer scale systems came into the picture. When we learn about wafers, we typically think, oh, this wafer is going to be diced and we'll have individual chips. Yeah. But then Cerebras came along and said, oh, maybe we can just pack a whole bunch of memory on the wafer. That way, getting access to memory is just like doing on-chip communication. You don't have to do this off-chip through PCIe or through NVLink. Then lately we have seen scenarios of designs where photonic communication is being used. Again, that started with chip-scale communication, but now we are seeing photonic communication being used on the wafer as well. So a lot of interesting work that has happened over the years.
What are some of the pros and cons of NVLink and NVSwitch? Why can't you just connect GPUs together infinitely?
As a network architect, I think from the perspective of what is the overall network bandwidth. That means if each GPU wants to talk to every other GPU, how much bandwidth can I provide? So going to 4 GPUs is fine, but beyond 4 GPUs, then you start hitting into the problem that, oh, these links are going to be shared. I won't be able to give full bandwidth to any GPU pair. I will then would have congestion. So then I'm not really using 100% of the capacity. And so it's not that trivial to just hook things up.
Ajay, another reason I was excited to talk to you today is because your team has made a massive breakthrough in fully homomorphic encryption, which I understand is a cryptographic technique that allows you to perform computations on encrypted data without decrypting it. Is that a good way of understanding it?
Today, when we are processing data, we typically have to decrypt it, and that makes it vulnerable to all kinds of attacks. With this new encryption technology, you can keep the data encrypted and you can process encrypted data. As an example, let's say I'm using ChatGPT, I type a query. Typically what happens today is the ChatGPT encrypts my query, sends it to the ChatGPT servers. In the servers, my query has to be decrypted. The LLM is seeing your data in non-encrypted form. That's the worry, in fact, that quite a few folks have, that I'm sending all this data, LLMs can see it. Can this be used against me?
If the LLM is now seeing encrypted data, does this require us to train new models, or this works with pre-existing LLMs?
Right. So we don't need to train new models. It's a question of just upgrading the model. So today, if the model is performing A plus B, it has to be upgraded to perform encrypted A plus encrypted B. So we don't lose out on accuracy. We don't need to retrain the model. It's just a question of giving the model additional capability to process encrypted data.
FHE in principle sounds perfect, but why wasn't something like this adopted sooner?
The math was invented back in the 80s. And if we were to look at how big are these ciphertexts and how much data movement we are required, we are looking at ciphertexts that were dozens of megabytes large. So back in the days, we didn't have the technology to handle that kind of data. Over time, chips became smaller. We had chips with larger cache capacity and all that. And so we ended up in a stage where maybe there was an opportunity here that, wait, now that the technology has caught up, can we make homomorphic encryption practical? And most of the people were thinking along the lines of, okay, looks like some specialized operations. Let's build an accelerator similar to how the TPU was built for machine learning. And a few companies started going down that path. My student, who is a co-founder now, she wanted to tackle that problem, and we said that let's look at it as a computer engineering problem. Right? Is the workload memory bound? Is it compute bound? Why is it slow? And When I say slow, I'm talking about really slow, right? 10 to the power of 5 slow down. And so we did the profiling and we realized that, hey, we are shipping these large megabyte chunks of data back and forth. That is slowing down everything. Our compute is sitting idle most of the time. How can we reduce the memory boundedness? Can we use techniques like prefetching? Or can we use techniques where we pack the data in a certain way to reduce the data movement? So several algorithmic ideas that came out, which led to reduction in the memory boundedness. And in parallel, we also realized that, you can't just use CPUs because the compute is not your regular A plus B. It's finite field arithmetic, which requires some specialized circuits. And so FPGAs were the right balance, which enabled us to do some custom arithmetic units and use the high bandwidth memory. That whole effort led to where we are today, where we realized that we have accelerated the compute far enough to commercialize it. To give you the number, 10 to the power of 5 slowdown back in the days, now less than 2x. So complete game changer, and that's where we are.
Cerebras has solved the memory bandwidth bottleneck for inference,
Yeah.
and your FHE work also targets memory bound operations.
Yes.
So do you see wafer scale architectures as a potential platform for accelerating FHE?
The biggest advantage of going to these wafer scale systems would be the fact that all my ciphertext, all the working set would be sitting in a big chunk of memory on the same wafer as my computer. So accessing all that data would become much easier. And so it won't be a case where my compute on the wafer is just waiting for data to be shipped from off wafer or off chip. Homomorphic encryption could become the default mode of operation for everyone.
There's growing concern about AI security. Where are you seeing the biggest demand around concerns around AI trust?
When I was in grad school, my identity got hacked. I started getting robocalls from collectors, and they said, several credit cards have been issued on your name. You have these many $1,000s that need to be paid. And I'm like, who gave you my information? That kind of scenario. And the credit card fraud is a very small situation. Today, the amount of data that we have out there, my data, my family's data, there are big concerns around AI trust. We did customer discovery where we talked to company CISOs, chief AI officers, and they see the benefits of AI, but they're worried that, hey, my data is going to go sit in the cloud. I don't know what's happening in the cloud. The cloud infrastructure provider has access to my data. Also, I don't necessarily trust how my employees are using my data. Maybe they have a private chat GPT running on the side where they will feed the data and get the answers. And so that's making these CISOs, chief AI officers, nervous. The common sentiment was, we like AI, but we don't trust it yet. But this approach of encrypted computing makes it easier for them to say that, okay, wait, you're going to encrypt the data, you're going to send it, nobody's going to decrypt it, they will still process the data and get me the response back. So this is a zero trust game. I don't have to trust anybody in the whole chain, but I can still extract value from the data.
I think one thing that's really interesting, especially right now, is that so many people are giving full access to all of their files, their desktop, to work autonomously. And I feel like the average person probably is not thinking clearly about what is the worst case scenario around safety and having their data protected. So can you talk me through how you're thinking about that?
This is a big challenge where individual consumers see the benefit of AI. Claude as an example, that I don't have to write code, I can just ask Claude to do it, but you are kind of giving away the keys to your kingdom by doing this. And so there needs to be a lot of awareness that needs to be built in from individual user perspective. Don't just give away everything you have. And going back to this, I mean, I'm saying this over and over, but this encrypted computing really opens the doors, really creates infinite possibilities on how we can take full advantage of AI without compromising privacy. I can see an ecosystem eventually where everybody is carrying their own private LLM with them.
What made you decide to go from research to co-founding Ciphersonic and take your research to market?
It was a case of opportunity. Not all research can be immediately commercialized. In this particular case, homomorphic encryption, people know it's like the holy grail of data privacy. And because we solved that really challenging problem, which had been around for 30, 40 years now, and in parallel with this AI boom, where there was a clear need for a strong data privacy and security guarantees, we thought that the time is right.
Has your teaching style changed since the rise of AI tools?
Changed a bit for sure. The way I look at it is that there is always this concern that, oh, students will use AI, everything will be done, we won't be able to grade things. Instead of worrying about what students will do with AI, let's figure out how we can help students use AI to become better at what they do. It's just like when Google came along, everybody thought, oh, all the answers are on the web, students don't need to come to class. So, same way.
Final question. Do you think you can tell when your students AI generate things that they submit?
For sure. Yeah. When you read the answer, the dead giveaway is when you start seeing hyphens in the answer. That's a giveaway. Plus, when you talk to the student, right, you immediately know that this answer doesn't line up with what the student is saying, the student's understanding. So yeah, it is a giveaway. In fact, there have been discussions that should we switch to oral exams. No written exam, just show up in the professor's office for 30 minutes, whiteboard discussion, tell me answers to these questions, and that would be a true indicator of whether the student really has understood.
Amazing.
Yeah.
Okay, well, thank you so much, Ajay. It's great chatting with you today, and I'm super excited to see where Ciphersonic goes.
No, thank you very much for having me.